So, orbital potential energy, we've just looked at how to put stuff in orbit, and what I've said is the reason it's so expensive is you've got to, first of all, get it high. That energy comes from the rocket fuel. And then you've got to give it kinetic energy. That energy comes from the rocket fuel. Hey, how much energy is that? Up until now, don't write this next bit down. Up until now, we have said this. Don't write this down. We have said potential energy is that. Why can't I do that as soon as we go cosmic, as soon as we start going really big distances, as soon as we start talking satellites and planets? Why is that wrong? Can anybody see it? Riley, what? It's only 9.8 on the Earth's surface and reasonably close, within a few hundred miles or so. But as you go up and up and up, it's going to change. So what we need to derive today is the cosmic potential energy equation, the one that works anywhere in the universe, the one that doesn't require the 9.8. How are we going to do that? Well, recall I wrote the area under a force versus distance graph. The area under a force versus distance graph is work. It's work. In fact, if I gave you a line that looked like this, where this was force and this was distance, and on this line I put a little point A and a little point B, this area here this is the work required to move an object from point A to point B. Now, if point A and point B were at different heights, that work would be mostly going into potential energy. But we said if we were on a flat surface moving from point A to point B, that object would have to be speeding up. It would have been picking up kinetic energy. But that was the work idea. You'll notice I can't just use force times distance either, because the force is a changing force. It's not constant. It's getting bigger. If we look at a graph of gravitational force, Fg, versus distance r, if I was to look at this, well, force is proportional to 1 over r squared. The r appears in the bottom of the equation, Bree, and it's squared. It really, by the way, is that equation there. For those of you who are in pre-calc 12, it's the reciprocal of a parabola. Okay? Have you guys done reciprocal functions yet in pre-calc 12 a little bit? Some of you nodding? They look like this. It looks like that. It's a curve. It's a curve. So consider the following situation. Suppose I have a graph of gravitational force as you're moving away from a planet versus the radius, the distance from the center of the planet. And I know that that graph looks like this. Let's put a point right here. Let's call it our Earth. I'm not putting numbers on here, but I guess from 0 to there would be 6.38 times 10 to the 6. I don't care. It's radius of the Earth. And let's put a point over here. Let's call it R final. This area here, this area is the work required to lift an object from the surface of Earth to wherever our final is. As a picture, Jacob, that's how much fuel, that's how much energy, that's how much work it would take to lift an object from the Earth's surface to a specific height. By the way, this is not putting in orbit, because as soon as you let go, it's going to come falling back down again. You haven't given it the tangent velocity yet. Here's the problem, Sasha. That's the area under a curve. We don't know how to do that. Who's in calculus? Okay, you guys have learned derivatives. Okay, in May, you'll learn the opposite of derivatives, and that's finding the area under a curve. Calculus was invented for two reasons: finding slopes of curves and finding area under curves. So you'll know how to do that around May. But for now, we're stuck. But we'd like to know this, but we're stuck. Okay, I'm going to show you a way to derive the equation. Technically, it's wrong. Technically, I'm doing some mathematical hocus pocus, but we're going to end up with the correct equation after we tweak it. Show you what I mean. So you agree with me, that's the area, but the problem is I don't have an equation for the area of a swooshy shape thing. So here's my proof. Since work equals force times distance, we can say this. Work equals gravitational force times radius. Now, if we're talking work against gravity, really, that's potential energy. Right? When you were doing work against gravity, and on the Earth, Riley, it was mgh. Can we go with that here? No. Hey, what is the universal equation for gravity? Hello, we've been spending lots of time. What's the universal equation for gravity? The equation. Big G, big M, little m over r squared times r. Oh, hey. Cool. This is going to give us our universal potential, our cosmic potential energy equation. And it looks like this. Equals big G, big M, little m over r. Except I have to add one more thing, and this is where the math breaks down. Look up. It's negative. And I wrote down here, why negative? Okay. It's negative because when you take the integral of the function with respect to r, you'll get a negative answer. Now, in May, those of you that are in calculus will actually understand that. In fact, you'll be able to derive this equation properly. You'll have the mathematical skills because it's an integral. That doesn't help right now. There's another reason it's negative. Where would you have zero potential energy? Now, what I mean by zero potential energy, is I mean if we let you go, you won't fall anywhere. Okay? And the answer is, technically, the only place that you'll have zero potential energy is at the edge of the universe, away from every single gravitational field. Infinitely far away from every single gravitational field. So the phrase we use here, Bree, is we say relative to zero at infinity. That's where this equation comes from. So we're going to define zero potential energy to be that way forever, or that way forever, that way, the edge of the universe. Okay? Now, to get there, to reach the edge of the universe, would you have to add energy to get there if you were in a rocket ship? Yes. You'd have to burn fuel. You agree with me? Which must mean that on your way there, you must have less energy than when you finally get there, because you're constantly burning fuel. You're adding energy to the rocket ship. Does that make sense? What if this is 0 now, and I've just told you that you have less energy on the way there? Hey, what numbers are less than 0? Negatives. We're going to define 0 to be the edge of the universe. In fact, the magic phrase, you can write this down. Draw a little arrow. This is, quote, relative to 0 at infinity. We're saying out at the edge of the universe, that's the only place where you can float in space and not feel any tug anywhere, not feel any need to fall, which must mean you have no potential energy. That's the definition of no potential energy. In reality, Roy, in the real world, instead of saying out at infinity, we'll just say a really long distance away, in which case you'll be so close to 0 that we can ignore the 15th decimal point or whatever. Okay, so why negative? Because we partly defined it that way. Out at infinity, I wrote, at the edge of the universe, an object would have 0 potential energy, since it's not being affected by any gravitational field. It can't fall anywhere. If our height is less than infinity, we have less potential energy. What numbers are less than 0? Negatives. So we use the phrase relative to 0 at infinity quite often as our hint to say, hey, use this one. Or, Matt, if we're talking cosmic things, use this one. Don't use MGH when you're in space. As an example. Matt, can you read example 1 to me, please, my friend?
How much work is done in lifting a 1,200 kilogram satellite from the surface of the Earth to a height of 1.2 times 10 to the 7 meters?
Did you say how much what? What's it asking us to find? How much work? Okay. First of all, work is force times distance. Can't use that. You know why? Because the further you go from Earth, the weaker the gravitational force gets. Force times distance only worked for a constant force. What was our second definition of work? Oh, work is also the area underneath a graph. Matt, do you see a graph here? No. Okay. For a candy, what was our third definition of work? We also called it the work energy theorem. That was the law of conservation of energy, which actually popped out of this. Jordan. Change in potential plus change in kinetic. Incoming, Jordan. Happy Valentine's. Now, you see the word lifting? What we're imagining, I guess, here is invisible little angels are picking up the satellite, or you can imagine the energy is coming from some kind of attached booster rocket that the question hasn't talked about. The only reason I don't like using the booster rocket analogy is the booster rocket would also have its own mass, and that would bleed off some of the energy. So my metaphor is all, because we're doing, again, bad physics to keep the math simple, I'm just going to say, let's pretend invisible angels are lifting it. No mass. Something is lifting it up. The hand of God, whatever you want to imagine, it's lifting it up. And all it's doing is lifting it up. It's just holding it in place. This satellite right now has no orbital speed because it's not in orbit. What that means is we're going to start at rest on the ground. We're going to end at rest in outer space. Okay? Leaves us with a change in potential energy. What's change in anything? Okay, so this is going to end up being however, I can't use MGH. Why? Because we're cosmic. This is going to end up being our new equation for potential energy, which is negative big G, big M, little m. And I guess the final is going to be R final. minus negative big G, big M, little m, over R initial. And I think R initial is going to be surface of the Earth. Here we go. Negative big G is what? Big M, 5.98 times 10 to the 24th. Double check, we're on Earth, yeah. If it was the moon, I'd put the mass of the moon there. If it was Mars, put the mass of Mars there. Mass of the satellite divided by, well, I notice in the question they didn't give me a radius, they gave me a height. So I think my final radius is going to be the Earth's radius, 6.38 times 10 to the 6th, plus the height above. That's the total distance from the center of the Earth. Is that okay, Ryan? Yeah? So far, so good? And you may notice, Ryan, in the middle here, I have a minus minus, which is a what? Plus. Ryan, what's on top of the second fraction? And next to it? And next to it? What's on top of the first fraction? Bracket, ditto mark, bracket, ditto mark, bracket. This will be one of the few times I'll allow you to do that, because you're going to find on the next example we'll be doing the most writing we'll do for any question all year long. Trust me. So we'll take not mathematical shortcuts, we'll take handwriting shortcuts. Also because I'm going to teach you to do this on your calculator the same way. All over our initial, hey, that's where we started. Where did we start? Surface of the Earth. Not 0, but what? All of you, get out your calculators. Every one of you, because I'm going to show you the best way to type this. The best way to type this is in stages. We're only going to type in the first fraction first. So you ready? I'm going to clear. I'm going to go negative 6.67, scientific notation, negative 11, times 5.98, scientific notation button, 24, times 1200, divided by bracket 6.38, scientific notation 6, plus 1.2, scientific notation button 7. Carefully type that in and see if you get that. Okay. And I'm going to write this answer down. I'm going to write it down to about 5 sig figs. So I'm going to go 2.6041 times 10 to the 10th. Negative 2.6041 times 10 to the 10th. And then a plus sign. Bree, did you have a teacher who went on a big rant at the beginning of the year about the usefulness of getting a good calculator? Yes? Then I'm fairly sure that all of you can backspace and bring back that same line, which Ryan astutely pointed out, the top is identical for. In fact, I think all I need to do is delete the negative in front and delete the 1.2 times 10. Just delete this. The plus, the 1, the decimal, that. And is that not the second fraction? And I would also say, is that not A, way faster, and B, less likely to make mistakes? Roy, what I'm going to say to you is be really careful typing in that first fraction. Read it 5 or 6 times before you hit enter. But if you get the first fraction right, we'll just tweak it to turn it into the second fraction. Because I'm telling you, the top will be identical except for the negative sign. Oh, and the bottom often will be nearly identical too. 7.5022 times 10 to the 10th? So now I'm going to add these two numbers together. Oh, conveniently, I already have that number on my calculator, plus negative 2.6041 times 10 to the 10th. Here's what I want you to notice. Even though we defined 0 out at infinity, even though we defined everything to be closer to be negative, you get a positive or negative answer. In other words, the answer is saying you're still going to need to burn fuel, to add fuel, to do work to get there. So the math, the physics still works. 4.90 times 10 to the 10th joules. And in case you're wondering, yes, that's a fairly big number. It takes a great deal of fuel just to get stuff up there. And again, this is not in orbit yet. This is just getting it up there. It'll come crashing back down like a meteor if this is all that you do. It would be like firing straight up. It would be slowing down, slowing down, slowing down, slowing down, slowing down. When it got to the top, it would come to a stop for a split second, and then it would start to fall back down, and by the time it got back to the Earth, probably be going fast enough perhaps to even burn up in the atmosphere. I don't know. I'd have to crunch some more numbers. How could we get it to stay in orbit? Well, we would give it potential energy, but what other kind of energy would we need to give it? Kinetic. Kinetic. Turn the page. I like example 2. Oh, I like example 1. I like example 1. I like example, but I love example 2. I love example 2. I love example 2. Example 2 also has a distinction. This will be the single longest in terms of the amount of writing question that you'll do all year. By a long shot. It will make momentum collisions at angles seem fairly tame in terms of the amount of writing. Thankfully, it's mostly plug and chug, but it's plug and chug along these, it's fairly horrendous calculator plug and chug. You ready, Sasha? What are they asking me to find? How much work? And there's another key word. Orbit. That means not only are we lifting it up, once we get it up there, we're going to get it going in a circle. Get it going in a circle. Well, work is force times distance. Why can't I use force times, not a constant force? Work is the area under a no graph. Jordan, what was our third definition of work? Not on your formula sheet. You have to commit it to memory. And Amanda, the fact that we're putting it in orbit sadly means none of these cancels. It's going to need both potential to get up there and kinetic to stay up there. I strongly recommend finding each of these independently. Amanda, what do you want to find first? The change in potential or the change in kinetic? I don't care. It doesn't matter. Change in potential? Okay. Change in potential equals, and what's change in anything, oh pray tell? Why is this next bit wrong? Don't write this down. Why is that wrong? Yeah, we're going cosmic. G's going to be changing. So otherwise, this question wouldn't be too much work. No pun intended. Negative, big G, big M, little m, our final, minus negative, big G, big M, little m, our initial. I said I was going to quit at 9:30. I'm going to try and finish this question. It's going to take us to about 9:40. I apologize. You're going to have homework, but that assembly kind of caught me off guard. I got to catch up for it. I think you have an assembly. It's either Tuesday or Thursday. I got to double check the calendar. It might be the following week, but this is when I can catch up. Okay. It's plug and chug time. Ugly plug and chug time, but it's plug and chug time. The amount of the change in potential energy is going to be negative 6.67 times 10 to the negative 11. Mass of the Earth. Oh, by the way, the word satellite is missing. I just always forget to put that in. Satellite. Space probe, whatever. Mass is 925. Now, did they give me for the final radius, did they give me in the question its radius or its altitude? Oh, so I don't need to add the radius of the Earth? A little nice. What's a minus minus the same as? And then I'm going to allow you to go ditto mark, ditto mark, ditto mark. Partly because that's exactly what I'm going to do on my calculator. I'm going to backspace and edit. And our initial, Earth. Going to do each one of these independently to about 5 sig figs. You know how lazy I'm going to be? Now, I can backspace several, and I notice that I already have the 6.67, negative 11, the 5.98. I just need to change these last few. 925 divided by... So you want to find out if your calculator lets you backspace several lines, that's going to be really handy. If it doesn't, as long as you can backspace one, great. If it can't, I told you at the beginning of the year. This is what I had in mind. You're going to be getting blisters on your thumbs from typing. You get 1 point, sorry, negative, Mr. Dueck. Negative, Mr. Dueck. I forgot to put the negative in front, but I can do it right now. Negative 1.419 times 10 to the 10th. Is that right? Plus, delete the negative, although I never put it in, so I'm okay. Oh, I just need to put the radius of the Earth here, 6.38 times 10 to the 6th. 5.7823 times 10 to the 10th. That plus negative 1.419 times 10. Of course, instead of going plus negative, you could just go subtract, but whatever. Okay, I get, are we getting the same answer? 4.3639 times 10 to the 10th? No? Yes? Yeah? Anybody else? This is lots of typing. So I'm totally willing to make, yeah? Okay. 4.3639. Put a box around it because, trust me, you'll have to go hunting for it later. Things I've learned. That's the change in potential energy. That's how much fuel just to get it up there. Now we want to keep it up there. Amanda, what do we need to figure out after the change in potential? Change in kinetic. Hey, what would change in anything be? So I'm going to go like this. We're going to, worst case scenario, we're going to start at rest. This is actually incorrect. This is actually incorrect. Actually, the reason NASA launches from Florida is the closer you are to the equator, the more kinetic energy you already have just due to the Earth's rotation, because the Earth is spinning. In fact, where would the best place to launch rockets from be? Right on the equator. Problem is, we don't have any large developed cities right on there. They have talked about building a floating rocket launch, like in the ocean, so you would truck it out into the ocean on the equator. The problem is, what else is on the ocean? Waves. So you can't have your platform doing this when you're trying to point a rocket at a, we haven't got the technology to do that consistently yet. This was one of the things that really handicapped the Russians, though, in the moon race back in the 50s and 60s. Do the Russians have access to anywhere nice and far south to launch from? No. The reason right now that we're using their rockets is they had to build rockets that were workhorses because they were launching from up north. They had to pour in a lot more fuel energy. So using the Soyuz rocket, the reason it's such a workhorse is because they were stuck with it. So just point of fact, we're going to go worst case scenario and allow the kinetic energy initial to be 0. Technically, it's not. We always launch in the same direction as the Earth's rotation to take advantage of the fact that we are actually moving. Hey, kinetic energy. I've been doing that since Physics 11. What's the equation for kinetic energy? A half mv squared. Which v? I think that. Right? Did they give me the mass?
Yeah.
Did they give me the orbital speed? Well, if I'm in orbit, I know that gravity equals centripetal. If I'm in orbit, I know that big G, big M, little m over r squared equals mv squared over r, where m cancels. Don't reach for your calculator yet. One of the r cancels. Now, I was going to get the v by itself. I was going to square root, but then I said, hey, wait a minute. Look at the kinetic energy equation. Is there a v there, or is there a v squared there?
V squared.
Matt, why don't I just leave the v squared by itself? And I think what I can do is I can literally plug that right into there, and the squared's going to vanish. That's v squared. V squared is big G, big M over r. The change in kinetic is going to be a half m big G, big M over r. Which r? Orbit. Which is going to be 0.5, 925, and I'm running out of room, so I'm just going to write big G, big M over, what was the orbital rate? 2.6 times 10 to the 7th. How many of you have calculators that can remember 3 or 4 lines back? Okay, you ready? I can't help noticing, AJ, that I have a G, an M, a mass, that, you know what? That there, what I've just typed, this expression right here is identical to this one, but positive and missing a 0.5. I can actually go like this. That's not it. That's not it. There it is! Except, I guess I need to multiply it by a half. Some of you may have to type the whole thing in, and that's fine too, but start taking advantage of good technology. If you don't know how to get more than one line back, read your manual. It might. Most calculators will allow you to do more than one line back. I know the graphing ones will do about 20 lines. I think I'll have to figure out on the Casios how to do it. Oh, you can go back and back and back? Okay. So find that one and just times it by a half. I think that's your kinetic energy. 7.0952 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.0952 times 10 to the 9th. The change in kinetic energy, 7.0952 times 10 to the 9th. Did I write that down right? Yep. What did we start out wanting to find in this question, Sasha? And we said, oh, it's the change in potential. That's in the black box. The change in kinetic, that's in the blue. Oh, now I can just add them together. It's going to be 4.3639 times 10 to the 10th plus 7.0952 times 10 to the 9th. Thank God I got one of these stored, this number at least, plus 4.3639 10 to the 10th. Answer. To put this satellite in orbit, it's going to take that many joules of fuel.
I thought it was 10 to the 6th.
What 10 to the 6th?
The potential, change of potential.
No. It's going to be 10. No, it's 10 to the 10th.
All right.
Oh. 10 to the 6th? Believe me, if that was the actual number, we'd have space stations several kilometers big already. Because that's not a lot of fuel. We can do that fairly easily. I'm sorry, to get a 925 kilogram cell, which isn't that big, takes that much. Let alone, think about building a 1 kilometer wide space station that would weigh probably several trillion tons. I don't know if we have enough fuel to do it right now. We need to find a different method. 5.07 times 10 to the 5.07 times 10 to the 10th joules. Okay. Thank you for your patience. That was a lot of me talking. Your homework is work on the orbital homework. There's good practice there.